Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Harmonic. We'll look at two seemingly disconnected problems for which the solutions have the same mathematical form. Who knew that stacking boards and collecting trading cards were connected? We'll start by stacking identical boards so that they hang over the edge of a table as much as possible. We first need to know how to determine whether they will balance on the table or crash to the floor. Well, this is based on center of mass. We'll be looking at boards made of a nice homogeneous material, so we'll assume that the center of mass is the center of the board. The rule is that something will balance if its center of mass is above a support. You can lean your body over without falling as long as your center of mass stays above the area of contact with the ground. Between your feet, if both feet are on the ground, your footprint if only one foot touches. For our board problems, the table is the support, so the boards balance as long as the total center of mass is over the table. So here's a nice rule for getting the boards to balance. If you have n boards of length L, hang the first board over by L divided by 2n, the second by L divided by 2 times n minus 1, the third by L divided by 2 times n minus 2, and so on with the last board extended by an impressive L over 2. Let's look at two examples and see why they exactly balance. To keep the arithmetic simple, let's say each board has length 1, and we'll put the edge of the table at x equals 0. If you have two boards, n equals 2, the rule says to hang 1/4 of the first board over and 1/2 of the second board over that. As shown, then, the first board runs from -3/4 to 1/4, 1/4 hanging over. Then the second board goes half beyond that, so -3/4 plus 1/2 to 1/4 plus 1/2, -1/4 to 3/4. The centers of the board's center of mass are at -1/4 and +1/4, which exactly balance at 0 the edge of the table. With three boards, the boards overlap by 1/6, 1/4, and 1/2. The boards go from -5/6 to 1/6, then add 1/4 to go from -7/12 to 5/12, and then add 1/2 to go from -1/12 to 11/12. The centers of mass are -1/3, -1/12, and 5/12, which again add up to 0. They balance exactly. In the picture, I've stacked up 8 boards. The overhangs are 1/16 of the length, 1/14, 1/12, and so on, with the last overhang by half of the board. Now, to be honest, I've fudged the overhangs a little bit. The table did not have a perfectly straight edge, and the boards are not perfect either. The long boards I used here are a little less steady than shorter boards, but the overhang effect is more impressive. So how far over the edge is that last board? Well, the length of the board, it's about 3 feet, times the sum of the overhangs 1/16 plus 1/14 plus 1/12 plus 1/10 all the way out to 1/2, which is about 1.36 times 3, a little bit over 4 feet from the edge of the table to the right-hand edge, and the left-hand edge is then about 1 foot beyond the table. It's pretty good. So what's the ultimate amount of overhang you could achieve with more boards? We'll come back to that in a bit. Here's a different problem, one that you may have wondered about if you've ever tried to collect a complete set of items one at a time. Suppose there are n items in a set. You buy one at a time, and each one that you get is random. That is, each item is equally likely, and the next one is independent of the one that you just got. How many should you expect to have to buy to get a complete set? Well, as with the boards, let's look at a couple of simple examples first. If there are 2 cards in the set, the second one you buy is different from the first, thus completing the set with probability 1/2. The second is a duplicate with probability 1/2, and the third is your missing card with probability at 1/2. So it takes 3 cards to complete the set with probability 1/4. You can see the pattern. You complete the set in 4 purchases with probability 1/2 times 1/2 times 1/2. That's 1/8, and so on. The expected value of the number of cards is the sum of the number of cards times their probability. So 2 times that 1/2 that we computed, then 3 times the associated 1/4 probability, 4 times its probability 1/8, and so on, which turns out you can show equals 3. For 2 cards, you'd expect to have to buy 3. Now, for 3 cards in the set, I had to look at the average in a different way to get the answer. Having bought your first card, how many cards would you expect to buy to get a second card? Well, one more card gets it done with probability 2 out of 3. Two more cards gets the second card with probability 1/3 for the duplicate, 2/3 for the new card. Three cards with probability a third, two duplicates times 2/3, and so on. The sum for the expected value equals 3/2. Now, having bought two different cards, how many more do you need to get the third card in the set? Well, one more card with probability 1/3, two more cards with probability 2/3, one of the duplicates times a third, three cards with probability 2/3, two more duplicates times a third, and so on, and that sum equals 3. So the total is 1 plus 3/2 plus 3 equals 11/2. Now the details are messy, but do notice that I had to approach the 2-card and the 3-card problems differently. Creativity is actually an important part of problem solving. The answer for a general number of cards is n times 1 plus 1/2 plus 1/3, and so on out to 1/n. Note that with n equals 3, this equals 3 times 1 plus 1/2 plus a third, which is 3 times 11/6, 11/2, just like before. So, why have I put these problems together in this episode? Well, here's our solutions. We've got the board overhang, L times the sum from 1/16 for 8. And if I factor out the L/2 and put things in the opposite order, L/2 times 1 plus 1/2 plus a third out to 1/8 for 8 boards. Number of cards, the general solution was n times 1 plus 1/2 plus a third, and so on out to 1/n. The same expression appears in both. 1 plus 1/2 plus a third plus a fourth, all the way out. If we ask the questions, how big can this get? We're asking for maximum board overhang, impressive, and maximum card buying, expensive. We give the name harmonic series to that infinite series, 1 plus 1/2 plus a third, and so on. The name comes from the form of overtones or harmonics in music. It's a somewhat disconcerting fact that the harmonic series diverges to infinity. Here's one explanation of that fact. The first two terms add up to 1.5. Two terms after that, a third and a fourth. Well, a third's bigger than a fourth, so you've got at least a fourth and a fourth, which is another half. Added in, the total is greater than 2. The four terms after that are all at least 1/8, so 4 of those makes 4/8, or another 1/2. So now the sum through 1/8 is greater than 2.5. The 8 terms after that add to more than a half, and the 16 terms after that add to more than a half, and so on. We need more and more terms to add in the next 0.5, but we can always have more terms, so the total sum continues to grow to infinity. If we had enough boards then, we could make the overhang as much as we wanted. There's no limit. That's pretty cool. And as the number of cards in a set increases, the expected number of cards to get a complete set grows, also without limit. That's not so cool. And fortunately, my parents didn't know this when I was collecting cards. The 2025 Topps baseball card set has 700 cards in it, with an expected value of buying 4,992 cards. I think I'll just order a complete set. But I love examples like this where the same mathematics applies to different situations. This is why it's important that mathematicians study abstract problems. They might be solving many problems at once.